Well, guys, we've made it. We are officially on the last lesson of the course. We're going to talk about the ideal gas law today, gas law number 6, and that's it. That's all. So what is an ideal gas law? It's a hypothetical gas that's made of particles that have mass but no volume and also no attractive forces between them. Now, we know that this is not actually in line with the particle theory, okay? This is why we say hypothetical. If gas is matter, well, it has to have mass and volume, not no volume. Particles, especially like even at gases as they're zipping around, do have attractive forces, not nearly as much as solids or liquids, but there are attractive forces there. But this is a lot like as you go on in science and physics, you'll learn a lot about situations where we're looking at the motion of an object in a vacuum because we have to take the air friction or the air resistance factored out of the equation. So our ideal gas says like, okay, in a very perfect situation, here's how gases will behave. And it's a fairly accurate representation for how gases behave on our planet. But the differences that show up, even though they're very small, are because of this volume that exists and attractive forces. Just to understand why we say hypothetical gas. So gas law number 6 is the ideal gas law. And the ideal gas law says that PV equals nRT. 4 of these variables you'll be pretty familiar with already. That looks like a lowercase p. It's an uppercase one. So we know that P is pressure. Now that we've used different units before, we're going to use kilopascals when we use the ideal gas law. V is volume. That's measured in liters, not milliliters, and I'll explain why we have to use these specific units in a moment. N is the moles of gas in, you guessed it, moles. T is temperature. Now this has to be in Kelvin. Looking before, you probably noticed that if you use Celsius, because it was all ratio based, it still worked the same. And you're not wrong, but I wanted you to start working on temperature in Kelvin because for our ideal gas law, we have to have it in Kelvin because of R. R is the universal gas constant. Why R and not U, G, or C? Because we ran out of other letters. So the universal gas constant is it's a value or a ratio that relates all of these together based on this ideal gas situation. So it has a value. It is constant. It doesn't change. It's 8.314. Now the unit is a little bit wonky. Kilopascal liters over mole Kelvin. These units here are specific to this constant. These units are why these other variables have to be in these units. If they're in something else, you have to convert. Have to. Okay? Well, you can probably figure out what we're going to do next. We are going to do a sample problem. Here's my question for you. Find the temperature, final answer is going to be in degrees Celsius, of 2.50 moles of oxygen gas that occupies 56.5 liters at 121.59 kilopascals. Let's fill in what we know. Our volume, 56.5 liters. Our pressure, 121.59 kilopascals. Our temperature, we don't know. Our moles, 2.50. You don't have to list R. I'm going to write it down just so we have it as reference. 8.314 kilopascal liters per mole Kelvin. if PV equals nRT, I keep making P small, I'm sorry. Well, we want T by itself, so we're going to divide both sides by NR, which leaves us with PV divided by NR equals T. Fill in those values. 121.59 kilopascals times 56.5 liters divided by 8.314 kilopascal liters per mole K times 2.50 moles equals T. And that gives us 330.5 Kelvin. If I track sig digs, I need to have 3 sig digs. So I'm going to round to 331 Kelvin is our temperature. Now, I asked for temperature to be in Celsius. So 331 Kelvin minus 273 Kelvin equals 58 degrees Celsius. Therefore, the temperature of the gas is 58 degrees Celsius. Congratulations, you've used the ideal gas law. We're not done. We're going to do one more problem. One that you'll say, oh, what? But too bad, we're doing it. Press pause if you need this, I'm moving on. This is the last example problem of our course, guys. Okay, I'm asking you, please determine the volume of nitrogen gas produced when 125 grams of sodium azide decomposes in an airbag to produce nitrogen gas and sodium. The temperature at the time is 27 degrees Celsius and the air pressure is 100.5 kilopascals. So here we are, combining stoichiometry with a gas law. How fun is this? Okay, first thing. Volume of a gas, well, we need to know the amount or the moles of the gas first. To do that, we start with a balanced chemical equation. Like so. Let's write our mole to mole ratio. Now we know the mass of sodium azide, which is 125 grams. I also happen to know the molar mass of sodium azide because I have a periodic table. So that means that I can determine the number of moles of sodium azide that decomposed. So 125 grams divided by 65.02 grams per mole gives me 1.92 moles. Awesome. So how many moles of nitrogen gas is that going to be? I have a 3:2 ratio. So it's going to be dividing by or multiplying by 3/2. Got Gotta get my calculator out for this one. 1.92. So I get 2.88 moles. That's how many moles of nitrogen gas is produced. Let's go back to the actual question. We want to know the volume. We're given temperature, we're given pressure, and now we have number of moles. We can use the ideal gas law. Temperature is 27 degrees Celsius, which is 300 Kelvin. Pressure is 100.5 kPa. Number of moles is 2.88 moles. And we're looking for volume. PV equals nRT. So V will equal nRT divided by P. 2.88 moles times 8.314 kilopascal liter over mole Kelvin times 300 Kelvin. I'm aware that it looks like this is only 2 sig digs right now, guys. We may need to envision that as 3.00 times 10 to the 2 Kelvin, right? Divided by 100.5 kPa. And that gives me 71.48 liters. And let's see my sig digs. I'm going to go down to 2 sig digs, which leaves me with 71 liters. Therefore, the volume of gas produced by the airbag is 71 liters. And with that, guys, I am done teaching you new material for the course. You've got a lot of gas laws to sort out. Once again, there is not a quiz or an assignment this week. I left it just for learning and practice. Please go do the gas law summary worksheet. So that's a Word document that I've posted in our content. It looks like this. So you can actually just sort out which of these you're using. So check off whether you're using pressure, volume, temperature, or moles, what the equation is. You can look at your reference for Kelvin, how to convert pressures in atmosphere, what STP is, what SATP is. Use this as a reference sheet while you're doing your quiz next week. And so next week I will have an assignment out for you. I'll also have a quiz. And then as of basically midnight on Thursday, so 11:59 p.m., we're done. Make sure you pop in to extra help sessions if you have any questions, and keep an eye on stuff because I do need to post a few more things for next week. Thanks a lot, guys. Bye.